so let's let it finish indexing. All right, so while that's cooking here, let's look at Anna's first. All right, so we're keeping track of culprit, pivot, parent, grandparent, and great-grandparent. Okay. Oh, we have two answers. All right, so answer one, determine which side is out of balance. Okay, got that. Special case for our out of balance side. Drop pivot onto parent where payload is equal to payload, the actual culprit place, right? Drop culprit onto pivot where payload is equal to payload, move right. If we have a grandparent, drop onto grandparent. If we have a if we don't have a grandparent, drop onto parent. Okay. To determine which side is out of balance, determine leaf node of the out of balance side. Special case, drop leaf node, culprit on parent, where payload is equal to payload, go to right, set pivot. Okay. That potentially could work.
Hey.
Let's we'll draw the picture. I'm sure we'll find something wrong with it.
Yeah. No. As long as you accept it.
Well, no, that's well thought out. I think I said last time it didn't have to be a correct answer as long as it was a well thought out answer, right? Because as we have already seen in exploring this, there are we're just going to click every blue box that it's just agree. It's going to leave this in a horrible situation. All right, so let's go back to our issue here. So let's clean up our tree a bit. So this guy is right, left out of balance, and something we were messing around with last time was the idea of, oh, well, maybe we need to do greater than or equal to the right and less than to the left, and did that make him a difference? It just created the same situation on the other side. Okay, so, and our situation arises in this case where we have two values that are the same, correct? It gets us into a tree that is technically an illegal tree. All right, so let's see. This is 1, 2, 3, 1, 2, 3, 4, 5. Okay, so this is out of balance. Where this would not be out of balance, right? 3, 4, yeah, that's not out of balance. All right, so this is out of balance, right, left. Now, the first thing we want to do in any of our cases is to get this guy turned into a right out of balance, okay? Which effectively means we're dropping this guy down here, which is our initially legal move, correct? So, because we're back to our original tree rules, which say that things to the left of our payload are less than or equal to the payload, things to the right are greater than. So that means if we take this guy and we drop it onto this tree, it's going to fall right here, as opposed to right here. Okay, now something to consider here while we're doing this is before, when we did our rebalancing, we specifically set this guy's right child equal to the, I guess in this case, this would be the grandparent, correct? To drop it down. This is the culprit, parent, grandparent.
Pivot.
Oh, this is pivot. Thank you. So this is parent. Yeah, culprit, pivot, parent, and then, gotcha. All right, so grandparent's the newer stuff. So we specifically took our parent and added it as pivot's right node, as opposed to adding it to pivot. Make sense? So this is an illegal tree. All right, that tree is an illegal tree. Not allowed. So we can't hard code that guy's right parent to that. But what if we did this? Draw a couple arrows here, since I'm not able to keep track of who these guys are. Here's our culprit down here. And then here's our parent. So this will be good enough for right now. Okay. And we know that those three will always exist, correct? We can't be out of balance without having those three guys. So they'll always exist. Historically, we went ahead and, well, let me go ahead and draw in a grandparent as well, because that does come into play for updating the next piece. All right, so those are our four guys. We're not going to worry about a great-grandparent for the moment. All right, so before, what we would do is we would take parent and just hard code it to the right child of pivot. All right, and that creates an illegal tree in this situation. But let's play this out. What would happen if I took parent and I added, so we're going to disconnect parent's left child there. And we're going to go ahead and add parent as a, well, we can even do this first as well. We'll disconnect parent's left child. We'll disconnect grandparent's right child and go ahead and hook it up to pivot, because pivot's going to be the new parent position. And then we'll take parent and add it to the tree that is pivot and let it fall wherever it's going to fall. So this guy would then drop down as a left child here, with this guy pointing nowhere. And let's shift this stuff up here. Okay, so parent is now down here. Culprit is up here. And then maybe what we decide to do, well, actually we can just leave it like that for right now. Oh, thank you. Pivot goes here. Okay, there we go. And this is parent. All right, so we did a shift by doing our add over and adding it to that node. All right, so is this a legal tree? As it currently stands, it's not a balanced tree, but is it legal? Yeah, it's legal. Okay. Looks just like the tree did before. We played a little musical chairs, but in terms of payloads, this looks the same. Now, if we were to ask this tree, are you balanced? The answer is going to be no. It's still right, left, out of balance. What's going to happen next? Well, we can just do the exact same thing again. If we call rebalance again, then our pivot and stuff like that is going to get reset. We effectively get stuck in an infinite loop, right? That would be culprit. This would be pivot. This would be parent. So this is a fresh call to rebalance. All right, so we've done an initial rotation, producing a legal tree, called rebalance again because we're still out of balance, and we're stuck with a tree that looks like this, that is a different tree than we had before, but is still a out of balance tree. Okay, so an upgrade from before is at least we're left with a legal tree. All right, so we can say that. But downgrade is we've introduced an infinite loop. So if I take this tree and I go ahead and I rotate this, again, I'm going to be stuck with, we're playing musical chairs here, right? Over and over again. Okay, so with that in mind, we now are not getting illegal, but we've decided that we certainly can't just haphazardly break this rule. Drop it there. At least not without cleaning up our act after the case, okay, after things are done. All right, so what can we do to remedy this? Right now we have two choices for rebalancing this that we've explored. Setting this guy's right child to a broken tree and then fixing it from there. Or doing what I just did, which is guaranteed to create an infinite loop in an event where you have matching payloads. So what do you think? Based on your solutions you gave here, what can we do to this code? Or do to this tree? This is our special case, correct? We already have our solution for non-special cases. I think that rotates out fine. We'll review that later, but certainly this guy is our problem child right now. Let me check back on this. Kill it and then restart it, because I think we should have the latest version of Java on here now. Okay, perfect. So it doesn't think that my Java is broken anymore. So then, out of curiosity, let's go ahead and run this guy. Oh, we can reinstall Hexam. All right, so while that's cooking, come back to that. All right, so what's our suggestion based on these solutions you have here? What can I do here? Is it legitimate for me to initially do this? I'm going to call this guy D0, D1, D2, just so we can kind of trace it through as we're moving things around, because these arrows are going to get in the way pretty quickly. Okay. So, is it legitimate for me to drop this guy down here as a starting point? This is an illegal tree, but we haven't bailed out saying that we're done yet. Okay? So I do that. So now we're sitting in an illegal tree. So let's keep track of our possible solution here. So our last time, changing the rules of our tree didn't fix anything. So step one is create an illegal tree by setting pivots right child to parent. Okay, we're going to say this is a right left out of balance. That's what we're solving for here. All right, so we'll create an illegal tree by setting pivots right child to parent. Done. All right, then we're going to set grandparents right child to pivot. I'm going to hit play again here. All right, thinks that guy is good. So we're going to, so that is grandparents right child to pivot. So if we have grandparent set its right child to pivot, else pivot is new root. We'll deal with that. We'll just say it for right now. All right, so we did that. Still an illegal tree, so we definitely can't bail out now. Now what? What do you think? Under no circumstances is this tree ever illegal, regardless of whether or not we change the rules or not. Okay, but we're sitting in this situation right now. we need this guy to move. All right. What would happen if, let's undo my rotations here. Oh, we forgot that doesn't work, right? So we'll go back to this situation. This is what it started off looking like, correct? What if we disconnected starting with our parent here, we just disconnected it from our list, like this. We know parent exists, right? If we're out of balance, we know culprit, pivot, and parent exists. So we're just going to break off that branch, okay? And we'll set our grandparent, if that exists, to whatever. Now, what would happen if I took the rest of my tree? Everything else. Well, let's just get rid of those arrows. Let's get rid of these arrows too. I think they're just going to confuse things for the moment. And I added it to this tree. First of all, is that possible? So at this point, I effectively have two separate trees sitting here, right? I have a binary tree that has these 3 nodes, and then I have a binary tree that looks like this. That's kind of a part of my old binary tree. So I've split my binary tree apart. Now I could take this guy, and I can now add him to my binary tree. How would that work? So A would drop to the left, correct? Drop to the left, drop right here. Is that guy out of balance? Very much so. Now, one thing we talked about before is that it's kind of important that we rebalance our tree after each individual addition. Because if we follow our old rules here, we can go through and we'd have to know what the bottom guy is that we added. So this would be the culprit that threw it out of balance, but there's things hanging off of this, so this might take us down a bad path anyways, but let's talk this out at least. If I went and rebalanced this tree, I can make an attempt at rebalancing. So that's one thing that we have to consider. Every single time we've done a rebalance, we always ask, are we out of balance afterwards? Because sometimes, especially if you've manipulated your tree into a situation sort of like what we're doing here, we may have to rebalance multiple times in a row to finally get back to a balance. Make some sense? All right. So, with that in mind, could I rebalance this tree? I can do my rebalancing algorithm, ask if the tree is still out of balance. I can then do my rebalancing algorithm again, ask if the tree is still out of balance, so on and so forth. I might have a little trouble, though, figuring out who the culprit is in this group, because I just added an entire tree. Right, so having said that, let's go back to, we'll leave that out. Let's go back to this tree. All right, now what would happen if I just decided this? We're going to take our culprit, break him off. He's the start of a brand new tree. And then I go ahead and I add my entire existing tree to the culprit. So now again, I have 2 subtrees. I'm going to take this guy. Culprit becomes the new root. And we're going to take A and we're going to add it to this tree. A would go to the left. Is this a legal tree? It's legal. Are we in balance? Nope. Nope. Very out of balance. Very left heavy. All right. Can we fix that? So the first starting point would be this. So we're gonna follow the rabbit hole here. How are we out of balance? We're out of balance. Well, we have to think about who was the last guy we added. Well, who was the last guy we added? From our perspective, the last guy we added was A. This guy right here, even though he has things hanging off him. So our whole algorithm that relies on pivot points and things like that now become broken. Now, having said that, could we discover what makes this tree out of balance? So could we start walking this tree? Right now we're relying on what the last node we added, what that guy was, right? But now let's assume I don't have that information and I have a tree that looks like this. Can I determine where the pivot is? How we're out of balance? Well, we know that the depth of the right side is 0 and the depth of a left side is a lot bigger than 0. Out of balance. All right, so we're focusing on the left-hand side. Now we want to know, how is the left-hand side out of balance? Well, the left-hand side is out of balance how? Well, we go down this route. We have a depth of 3 here. We have a depth of 4 here. How is this guy ultimately out of balance? Or is this a whole new kind of animal? We're definitely out of balance left. But since we've lost the idea of the culprit, we don't know where that guy lives to tell us how we're out of balance. So the question is, can we discover that? Historically, our out of balance, our culprit was always which node? The node that was the deepest on the side that we're out of balance, right? All right. So in this case, we can determine that we're out of balance to the left. That is still a judgment we can make. All right. So now we need to decide who the culprit might be. So let's assume we did the, we're going to go down the left-hand side. We're going to find out what the depth of the deepest leaf node is here. So that's going to be this guy. And then we'll find out what's the depth of the deepest leaf node here, and that's this guy. So we're going to assume this is the culprit, this is the parent, this is the grandparent. Okay? So can we fix that? Again, we're just searching for the deepest leaf node on a side of a tree. So this is out of balance left. Let's see how, from this guy's perspective, this is what we're fixing. If this is out of balance and we want to rebalance this little world. So one of the things we talked about before, and one of the reasons we're doing this as a tree of trees, is we can look at individual parts of the tree independent of the rest of the tree. Make sense? And possibly rebalance that. Something we should keep in mind for this larger solution here. So if I'm only looking at this tree, we can say this guy is out of balance, correct? And we're going to say we want to rebalance just this tree. Okay, so we'll fake disconnect him for a second. So this is a tree whose left is nothing and whose right is a depth of 2. He's out of balance right, left. So what are we going to do? We're first going to turn this into a right out of balance. So that'll do that, row. And then, actually, hold on, right out of balance, it'll be, so the first thing is we need to turn it into, this is right, left out of balance. First thing we need to do is turn this guy into right, okay, which again is our illegal move. And then do what? Rotate this guy down, and once again we have an illegal tree. So rebalancing that micro tree doesn't fix our problem either. Okay, well, so let's go back, but still keep in mind that any tree in our larger tree can be rebalanced in and of itself. All right, so we can sit there, almost think of it like a Rubik's Cube. When we can't get a solution for the current state of the tree, we can recreate our tree into something else that might be able to give us a solution. Remember way back when I introduced AVL trees, I mentioned that rebalancing is very expensive? Now the hope is when we do a rebalancing after each add, the number of manipulations is minimized. Okay? But let's see how far back will this let me go. Okay, that will. So one more. All right, that's our current out of balance tree, right? In this case, we know that one side is deeper than the other side by 2. All right, so we don't have a tree that's that out of balance. The second we started adding things to our top level root node, we created a whole new, I guess, broken tree where we had no way of backtracking. But now this is a tree. This is a tree. This is a tree. So on and so forth. How far up in this tree do we need to go before we have an opportunity to create a legal tree that is in and of itself, I guess, in balance? What if we focus on the other side? We know that this tree is out of balance to the right. And we know that we've just done an add. So at most, it's out of balance by 1 level. So that means we know the left side of this tree is not that much shorter than the right side of the tree. Fair enough assessment? All right. So if we just notice that one of our issues here is that the larger tree, if we do this whole add to the root thing, we create a tree that could be very out of balance on one side. In fact, is pretty much guaranteed to be very out of balance on one side. What if we disconnected the entire left subtree? Split our tree again. Okay, so now I have 2 separate trees. Similarly, we know that these 3 guys always exist. So let's disconnect again. In fact, here we can disconnect like this for right now, and then we're going to disconnect again. So let's keep it as 3 separate pieces. Okay, so we have our root node of our tree up to, but not including our parent. And this supposedly might not actually be a tree. Because we could have a micro tree like this that's just barely out of balance. Could just be 3 nodes that happen to all go in the same direction. So this is a potential tree. This is also a potential tree. And then this is the subtree that needs to be rebalanced. This is our problem. That tree in and of itself, if that's all we were looking at, cannot be modified in and of itself. It's impossible to rebalance that tree following our rules, unless we change the rules, but then we can create a scenario on the other side where it would be impossible to rebalance that tree, okay, because it breaks the rules of a binary tree. So how can we modify this guy only to allow us to rebalance this tree? We need to change the state of this tree. In its current form, it's not balanceable. So we need to add something to it. The question is, what do we add to it? We know that all the stuff up here would go to the right of this tree, don't we? Everything would go to the right of this tree. Remember, I've disconnected the the original left subtree. So if we added everything above, which could be null, to this tree, actually, could it be null? If we just had actually, that's probably the thing to look at before we do this, but so pause this for a second. Let me just do this example. This goes back to our left example. Let's say that we had a tree that looked like this. it wasn't out of balance at that point in time. Depth of 0, depth of 1, everything's fine. We added another D, and now it is out of balance. How do you balance this tree? So we've broken it down to a nice little mini case. Is it possible? That's my entire tree. Is it possible to balance that tree? I mean, the shape of a balanced tree says that the left side can't be more than 1 depth from the right side. So in terms of creating a shape, our only solution is that. Breaking binary tree rules. So follow-up question would be, I have a tree. The tree is out of balance. What does that mean? Why do we care if a tree is out of balance? What are we trying to accomplish by rebalancing a tree? Go ahead. Yeah, we're trying to keep the tree as optimized as possible for searching. All right, now looking at this little microcosm, this tree right here is as optimized as we can make it right now. So the question is it okay to say this tree cannot be rebalanced? Short answer is it better be. That better be an acceptable condition. So we're going to say we did our best. We marked culprit and pivot and parent and all that stuff. We looked at everything and this isn't going to work. How did we determine that it wasn't going to work? So we're going to build another little algorithm here. Is rebalancing possible? We want to be able to determine whether the current tree can be rebalanced. Now that we've proven that there are situations where even a simple tree, without all the extra confusion, could be unbalanceable. So how will we ask that question? This is culprit, pivot, parent. I mean, we could have a tree that looks like this. Would this be rebalanceable? How? Yeah, that's our normal left-left rebalance, correct? We didn't do anything special there. That's how we rebalance left-left. Is that tree rebalanceable? Same reason. All right, so how did we know that this tree is not balanceable? Okay. Let's see, can we create a scenario where one of them is different, but it's still not balanceable? I don't think so. So if the payload of culprit, pivot, and parent are identical to each other, this tree is currently not an illegal tree, but it's as balanced as it's going to get. Seem like a reasonable assessment? Oh, look at that nice little icon.
There's the upgrade right there.
Boom. Oh, what's this stuff? Look at that. Boom.
Can you change the color of the Android too?
Well, you could do that through the interface thing. Oh, you could take screenshots. What are these guys? Just. Oh, that's bad. I get it. I thought it was just shapes to play with. That's actually not so bad. All right, so let's go back here. Is rebalancing possible? No. If culprit, pivot, and parent have identical payloads, then it's not possible. Let's see if that holds up back here. All right, this is our right-left out of balance tree. So culprit, pivot, parent all have the same payloads. If this was B, is it fixable? Yeah, it's fixable. So seems to hold up there, at least with a cursory look. So if we were trying to balance this tree after we've determined it's right out of balance, then left out of balance, this is right, left. If I look at my three variables, and we know all three of those exist, we cannot have an unbalanced tree where parent is null. Correct? So we have to have at least two levels down so we know that these three variables have stuff in them. All right, so we can ask that question. Pretty simple question. You know, is there anything we can do about it? Yes, we know it's out of balance, but how do we fix it? Well, in this case, we can't. So we just leave it alone because we cannot take that first move. So we come back and we say, tree's out of balance. I've done what I can, which happens to be nothing. All right, so our rebalancing algorithm would say, let's go back here to this. If rebalancing is not possible, return. Else, well, let's keep it up here. Create right, then perform the normal right fix. All right, so we already have a solution for rotating right, and left. But does our solution currently take into consideration a not allowed to rebalance? Yeah, so those guys aren't quite complete yet. Leave it like that for a second. So let's go back into our binary tree. Let's go this route. And let's go that route. All right, so here is our rebalance algorithm. Figure out how we're out of balance. So left, we are finding out if we have a grandparent. If we do, we're just setting the pivot. That should put us, we're resetting the tree of the grandparent to our pivot. Else, we're setting the root of our thing inside of BST core, so those guys can be used inside of our rebalancing algorithm. So we're keeping track of the, let's see, this was after the add. So when we added, that's in binary tree, we're setting those guys up, right? We're keeping track of grandparent, parent, and pivot. We know, like I said, parent definitely has a value in it. We know pivot definitely has a value in it, and culprit will also have a value in it. So those three at least will. So when we go back to BST, If we're out of balance left, we're asking if we don't have if we do have a grandparent, then go ahead and set our grandparent's left tree to our pivot, dropping it back into position. Let's see, if we do that to pivot, nothing breaks there. Otherwise, we'll set the root to pivot, one of those two, and then we clean up parent and pivot to have their pointers in the right place. We're only doing any of this in the event that we can actually do anything. So we need to now put in our check for can we rebalance. So we'll make this a private function, Boolean can rebalance. And this guy is going to return a true if we can and a false if we can't. So our Boolean here was BST core dot culprit dot get payload is equal to BST. Let's just steal this since I'm not, well, we'll practice. Dot pivot dot get payload and BST core dot culprit dot get payload is equal to BST core dot parent dot get payload. This will boil down to a true if this is not rebalanceable. Okay? But we have something called can rebalance. So we want it to be true if this is false. So we're going to not all of that and return it. All right? So this says if it's true that all of those things are true, that means it's not rebalanceable. So if this is true, we'll not it to turn it into a false. This guy will then return false. This tree is not rebalanceable. Make sense? All right. So this is our check for can rebalance. So after we've determined we're out of balance, we're then going to determine how are we out of balance. Now, we actually don't even need to ask that question yet. We don't need to waste our time determining how we're out of balance if we are indeed not rebalanceable. So we're only going to do this if this dot can rebalance. So we're only going to do all of those things. Let's see, we probably want to take that out of play because there are now situations where it will still be false. So testing to make sure the tree is fixed doesn't get us anywhere. Oh, that was nice. See that? Re-indented automatically. So we might be catching up. Emo saw some iOS stuff last night and seemed to be in awe. How many of you in here have done some iOS things before? I think just you from the watch class. Isn't iOS like so much better than the Android crap? But hey, this is another point. This is a plus plus, right? Auto-indented. Xcode doesn't do that. It's garbage. Might as well just be using a paint in bathtubs or something. All right. Well, you know, I found in the cafeteria they have pre-bubbled water. Yeah. They have seltzer water, one of the, yeah, I didn't know they had it on one of the soda machines. Can't get any, I mean, that's pre-bubbled water. It's the one near the salad bar.
Don't tell them, let them figure it
Huh?
out.
Omelets now too.
Tuesdays and Thursdays, yep. What's this?
I said I wouldn't get it. This stuff's awful, but I've never seen it.
What, seltzer water?
Yeah.
Well, it's not, I mean, it's only awful if you just drink seltzer water. Put some other things in it. It could be kind of decent. Put a little umbrella afterwards. All right. So we're only going to do this crap if we're not wasting our time. Okay? Only if we're dealing with a tree that can be rebalanced are we going to do this stuff. All right. Fair enough. That's our first step. Otherwise, we won't waste our time. So now let's go back. So we've introduced a new concept to our world of rebalancing trees. Sometimes we can't. So now let's go back here. We're going to determine that this tree is not rebalanceable. So let's add something else to this tree. We've done what we can. It's a little bit out of balance, but it shouldn't be that bad. Okay, but we want to make sure that we can bring things back at a later point in time. So let's go ahead and add a new dude to this this tree. And well, we know we're gonna, if by sheer bad luck, if we keep adding more D's to the tree, we're going to get a very unbalanced tree that's not repairable. So let's pretend like our errors weren't compounded there. So we're going to go ahead and let's add a, let's just change these all to E, just so we can create the gap here. Then we'll try to add a D. So it's going to go right, it's going to go right, it's going to go right. Okay? Is that right? C, D, E. Oh, it would be. We need one to go. Well, that's fine. It would. This will balance that way. I wanted to give us a rotate that way. So we'll see our break over here when the left side's actually deeper, but we have a culprit on the right. We'll create it here shortly. Okay? So now we have a tree like this. We are out of balance. We're out of balance right, left. We ask the question, is this tree fixable by our current algorithm? Current algorithm asks, can we rebalance? Well, it says if this guy is equal to this guy is equal to this guy, we can not rebalance. But one of these is not equal. So by our current algorithm, can rebalance would return a true there. And what would rebalancing end up having us do? Would have us try to drop this guy down here, making an illegal tree. All right, so we need to update our algorithm. Algorithm now says it's just the pivot and the parent that need to match. The culprit really isn't part of the story. Okay, well, that makes it kind of easier, actually. So now we can come up here, and we're going to say pivot, and we're going to say parent, and we're going to dump the and, just like that. So if pivot and parent's payload are the same, that's when we can't rebalance. All right, fair enough. So still out of luck here. We added the D. Let's see, how can we give ourselves I want to get something over here. So if these guys were all D's again, and then we added an E. E goes to the right, E goes to the right, E goes to the right. Correct? Okay. There we go. So now, here's culprit. Here's pivot. Here's parent. So, how would we fix this tree? So this tree says we're going to, we're out of balance right. That's what we would determine, correct? Based on where culprit is. Okay, we're out of balance right. All right, is this fixable? Is pivot and parent different values? It is. So by our current check, this guy is fixable. All right? And how would we fix it? We would do a right rotation. All right, so this should be our easy guy. Now remember, this is pivot. It just so happens that pivot has some stuff hanging off of it that we might not necessarily be used to. Okay? So, first thing we're going to do, let me grab these guys. So this is pivot. So we have a hold on to this guy. Is we're going to go ahead and add our culprit to our parent. We're going to add it. So we want to move away from this idea of hard coding setting left and right children. So that starts becoming problematic. All right. So if we add E to our parent, it would drop into the right-hand side here. Right? It effectively will do what we kind of wanted it to do by just setting that guy's right child to this. But we accomplished it using our built-in functions for adding things. Okay? Now, one issue to consider there, though. The second we call add, what do? We start messing up our global culprits and things like that. So that means we probably need to bring those guys local. All right, so let's go back to our rebalancing algorithm. Rebalancing, step 1, make local copies of culprit, pivot, parent, and grandparent, as we may be adding things which will break the BST core versions. Okay? So far, so good?
I'm kind of confused on that tree. Like, how would it be out of balance that would E be a culprit when I was like that? Because the D would be the culprit because it was the one that like took you out of balance. I don't understand how the E would.
This was down here, right?
Yeah.
Well, it would be our culprit for right now, because of the way we're adding stuff to our tree, we're tracking the last guy that was added. So when we add, so when the tree looked just like this, we decided we could not rebalance this.
Oh.
Okay. Then we added the E, and it started, plinkoing down through here. So this was culprit, this was culprit, this was culprit. Finally landed here, culprit, pivot, parent, because that's how our add works. Sets those globals. All right, so we're going to detect that this guy is out of balance right for rebalancing it. Okay, so we're going to go ahead and preserve those local variables, because when we re-add something, so re-adding it to the tree rather than hard coding left and right children is really a safer bet. We should get the same results that we were expecting, but it should be safer for us to do as long as we remember culprit, pivot, and parent and grandparent, because there are going to be some situations, especially now when we're dealing with a tree that might be more unpredictable than it was before. See, before everything was peachy because we were operating under the assumption that we could always rebalance the tree, and since we could always rebalance the tree, what did that translate to? It's like, well, whatever we have right now is what it's going to be, so we can directly manipulate left and right and all that jazz. Okay. So we're going to go ahead and we're going to take, we're going to fictitiously, I guess for right now, disconnect this tree. So this is pivot effectively points to the root of this tree. Correct? This top D is pivot. So right now we have a string tied to this guy, which marks the root of this little subtree as pivot. Now what we can do is we can go ahead and add culprit to parent, which would drop it into this position right here and set the appropriate right child to it. Okay? Overwriting the right child that used to point here. Okay? but we still have a rope tied to this guy through pivot. So we haven't lost him. We still have a pointer to this guy. All right. Now what do we do? So now I have this tree. What can I do with this tree? If I add it back to parent, where's it going to go? Here? Does that rebalance anything? Let's go back to this look here. We know this guy's out of balance right from our perspective. And what do we do in a right situation? Well, we should be doing this. Should look like that. Correct? Okay. So, how did we get it back to that position? Well, we moved this subtree out of the way, just visually. We added culprit to parent. Then we added pivot to culprit. Make sense? Is this a legal tree? Still out of balance. We can't fix it, right? This is going to haunt us, right? We have a portion of our tree that's out of balance, and it's an unfixable portion of our tree. So we almost have to think of this little subtree here as just a roadblock for us getting our tree completely into balance. Okay? So before, our tree looked like this. So it was out of balance by, it was out of balance by a level of 2. But now when we rebalance this guy, we drop this down, we move this up. It was a pretty clean algorithm. So let's think about that rebalancing. So we took culprit, added it to parent, and then took pivot and added it to culprit. Make sense? So that was right rebalancing. Let's go back and look at our right rebalancing. Okay, so this was us determining whether or not we had to update our parent or not. But again, we're directly setting right trees to things. If we're setting pivot as the right tree of grandparent, shouldn't we just add pivot to grandparent? It should drop into the right tree, correct? But before we can do that, we need to go ahead and store those local variables. So int culprit is equal to bst core dot culprit. These aren't ints, these are binary trees. Binary tree pivot is equal to bst core dot pivot. Binary tree parent is equal to bst core parent, and binary tree grandparent is equal to bst core dot grandparent. All right, so we'll bring those guys local. So now when we ask these questions, we'll do it for right first. We're not asking bst core. We're asking our local grandparent if it's not equal to null. Then we're asking our local grandparent, and instead of setting his right tree, we're going to add pivot, which should drop it into place. This guy should be okay. The tree doesn't modify, so we don't need to give ourselves a local copy of that. But we will update the root in that case to pivot if we don't have, or if we do have a, or if we don't have a grandparent rather. If we do have a grandparent, we add pivot. Otherwise, we update the root. Okay, now here we're setting our right tree to null. That one's okay, right? Because we're disconnecting it, if you will. Then we are adding our parent. So we're gonna say parent.setRight to null. We're gonna say pivot.add parent. All right, so we're updating, doing adds instead of, oh, I just noticed something I hate again. When it re-indented, it also moved all my else ifs up. Ugh, garbage. Okay, so we just finished right. Let me put a note in our notes here. To do update left, then implement left, right, and right, left. All right, so we'll no homework. We'll do that on Thursday.